Hello, everyone. We are going to continue with lecture 5 today, and we are going to talk about elementary matrices and the method of finding A inverse. In the previous section, we learned that matrices can have inverses, so they have special properties, but I just gave you a method of finding inverse of 2 by 2 matrix. In this section, we are going to learn how to find inverse of any matrix, well, under condition that inverse exists, of course. To do that, we are going to start with definition, and you see that the section is named as elementary matrices and the method of finding A inverse. But again, that's not going to be the only method of finding A inverse. We're going to start with definition of elementary matrix. So, definition. We are going to define elementary matrix as matrix E, and that's going to be a square matrix, n by n. And elementary matrix can be obtained from identity matrix of the same size by one elementary, by one elementary row operation. So I'm going to show how it works on like different examples, but I'm going to consider 2 by 2 examples. It's going to be just a little bit easier to write them down. So for example, well, for first 2 by 2 matrix, which is identity matrix, is going to look like 1, 0, 0, 1, right? This is going to be 2 by 2. Now, we know 3 elementary row operations, right? And I'm going to kind of write them down. Number 1, well, I don't know. Let's start with exchange of the rows. Exchange, I'm going to write it just exchange. So exchange means that I put the first row into the second one and the second into the first. Just this is an operation. Now, how corresponding elementary matrix is going to look, and I'm going to label it E1, first one. But this index 1 is not going to reflect the size of the matrix as we usually use like double indexes. It's going to reflect just a numeration of elementary operations. So this one is similar to this one. So if I exchange rows in my identity matrix, how matrix is going to look? Well, it's going to be a matrix with exchange rows. So this is going to be my first elementary matrix. Again, 2 by 2. Second elementary operation. Well, we can multiply like row by any like non-zero number, right? Multiply by number A. Like I'm going to write down how this elementary operation looks and then write down how elementary matrix. For example, I'm going to multiply row number 2 by some number. Well, I'm going to write down the result of multiplication. And again, this index 2 means that it's a second like elementary matrix, it's not showing the size of the matrix. Row number 2. Well, what can we choose as a number? Well, let's choose A equals, I don't know, 2. So how it's going to look? Well, we need to copy identity matrix and multiply row number 2 by 2, right? So it's going to be 1, 0, 0, 2. That's going to be like elementary matrix. Kind of nice, right? And the last one, number 3, is going to multiply like one row by a number and add it to another row. Multiply and add. Oh, again, I'm just trying to make it shorter. I don't know. Well, yes, I'm going to choose something just for example. So I'm going to take row number 1 equals row number 1 plus 3, row number 2. Well, just as example, how my elementary matrix is going to look. If I take row number 2 of this identity matrix multiplied by 3, I'm going to get 3 over here. And if I add it to row number 1, I'm going to get next matrix 1, 3, 0, 1. So, while we do have 3 examples of possible elementary matrices, and they are only elementary matrices possible. So, they just correspond to elementary operations. That's it. Well, numbers can be different, and if your identity matrix is bigger, of course, you don't have to exchange only row number 1 and 2, you can exchange any rows, but that's basically how they look. Now, guys, let's set up a theorem which is going to tell us like how are we going to apply these matrices. Theorem. If the elementary matrix E results from performing a certain row operations. Uh, operations on, sorry, of on, pressing on off, on I am. This matrix has a square matrix, identity square matrix with dimension m by m. I'm going to put just one m because the second index is also m. And we have arbitrary, sorry, a m n, then the product of that elementary matrix by A is resulting by same operation. Think by same operation on A. Well, kind of looks long, but let me explain you. So we can do two different things on matrix A. First, we can do a row operation, one of 3 elementary row operations. Second, we can take matrix A and multiply it by elementary matrix, which is kind of corresponding to that row operation. And the theorem tells that the result is going to be the same. So row operation and multiplication are going to result exactly same. Well, I'm not going to prove this theorem. I'm just going to show you how it works. And I don't think that we really need like any special proof of the theorem. Let's see how it works actually, because kind of proof is very, very obvious. I'm going to consider matrix A again, 2 by 2, just to make it faster. And I'm going to consider our standard matrix 1, 2, 3, 4. Well, I don't know. I'm going to use elementary operation of addition of 2 rows. Well, again, it's not necessary to do this specific one, but I'm going to just. So my elementary operation is going to be row number 1 equals row number 1 plus row number 2. Well, generally speaking, I'm multiplying row number 2 by 1 and adding it to row number 1. So this is type 3 of elementary matrix, multiply and add, right? So this is how row operation looks. How elementary matrix is going to look? Elementary matrix is going to look how? Well, if I just add two rows, let's look at identity matrix of 2 by 2. I just add row number 1, row number 2. I'm going to get elementary matrix representing this operation or similar to this operation is going to look like 1, 1, 0, 1. So take row number 1 and add it to row number 2 and put back the result into row number 1. That's how elementary matrix is. Well, now let's look how this operation is going to affect the matrix. And then let's look how EA is going to affect the matrix. So kind of do two things. Well, first, how row operation is going to affect the matrix. Well, the matrix is going to become next. If we add row number 1 and row number 2, 1 plus 3 is 4, right? 4 plus 2, well, maybe I should just keep actually writing down like as it is. But I'm not going to actually simplify it. I'm just going to write it down. 1 plus 3 over here and 2 plus 4 over here. And row number 2 is going to stay as it is. So this is a row operation. Row operation. On this side, I'm going to do a multiplication. So I'm going to multiply actually 1, 1, 0, 1 elementary matrix by matrix A. 1, 2, 3, 4. My 4 doesn't look very 4. Looks like 1 actually. How my product is going to look. Well, I'm going to start multiplication by multiplying this row by this column, and that's going to be what? 1 by 1 and 1 by 3, right? So I'm going to write it down. 1 by 1 plus 1 by 3. And that's going to be my first element. My second element is going to be the very first row by the second column. It's going to be 1 by 2 plus 1 by 4. What is going to happen next? Well, if I multiply the second row by the first column, remember, because I have 0 multiplied by first element, 1 by 3 is going to just give me 3. And the same is going to happen to the 4, 1 by 4. Now, let's compare our results here and here. Well, first, let's start comparing 1 and 3. You see, it's obviously they're still 3 and 4. It's still 3 and this is still 4. Why does it happen? Because this number is exactly 1. If it was not 1 and this number is exactly 0. If it was not 1, it would be different numbers. But since it's 1, that's always going to be the same. And why it's 1? Because this is modification of identity matrix. It was 1 in identity matrix, right? And we don't modify this number because we are working with a different row. Now, let's look at the first row here and the first row here. Well, first, it looks like we do have 1 plus 3 and 2 plus 4 here, and 1 by 1 plus 1 plus multiplied by 3 and 1 by 2 multiplied by 1 plus 1. Well, but we understand that multiplication by 1 is not changing the numbers, and we still have this same 1 plus 3 here and 2 plus 4 here, which is exactly what we have here. Why does it happen? Well, it happens because in my first row, in my elementary matrix, I have two ones. Why do I have two ones? Well, the first one is just original one from identity, right? And the second one, it's actually the operation we did, that addition of the second row. It's necessary must be 1, but if it was 2, for example, or 3, we wanted to add 2 or 3 second rows, we would have these 2 appearing over here too in these two elements. Like in this element and this element, we're also going to add like not just 3, but 2 multiplied by 3 or 4 multiplied by 3. And over here, the same is going to happen because if you do this elementary operation, like not, if you place over here, for example, 3, then this number is going to be 3. And this number is 3, and this number is 3. And over here, you are also going to have extra 3 and extra 3. So you see that the result is going to be exactly the same. What we are trying to do in this theory, we are trying to transfer a row operation, which is basically made in words, right, into the area of multiplication of two matrices. which is kind of more mathematical way to write down a row operation. Why do we need this? You are just going to see it in a minute. But before we move to like more complicated stuff, we want to talk about inverse row operations. So let me move everything up. Inverse row operations. What are inverse row operations? Well, generally, inverse row operations are kind of returning back to original matches. Well, I don't know. For example, if your row operation was row number one, exchange to row number two, inverse is going to be row number two, exchange to row number one. If your row operation was, I don't know, for example, multiply row number 2 by 3 and add it to row number 1. What is going to be inverse? Well, inverse is going to be take row number 1 and subtract 3 row number 2. So basically inverse row operations are kind of eliminating the previous step. Like if you took second row, multiplied it by 3 and added to first one, now if you took a second row multiplied by 3 and subtracted, it's going to return you to the previous step. And what else are we missing? Just multiplication. Well, let's kind of represent the last one. Imagine that row number 1 is like 5 row number 1. You decided to multiply whole row number 1 by 5. What is going to be inverse? Well, inverse is going to be multiply row number 1 by 1 over 5, right? It's going to eliminate the result of multiplication. Well, these are inverse row operations for which you also can have elementary matrices. And just because inverse row operations are also row operations, like exchange of the rows. Well, this is row operation of exchange of the rows. Or multiply row by number and add and subtract to another one. That's also elementary operation. And the last one, multiply by a number, it's just like not 5, but 1 over 5, still number. So it's still elementary operation. So they can have elementary matrices. And these elementary matrices are going to also perform inverse steps. So for example, I'm going to consider this last one. If you did this operation and elementary matrix was looking like this, I'm going to kind of label it as 5, 0, 0, 1. That was elementary matrix, which is similar to this operation, multiplication of the first row by 1, right? Then inverse elementary operations. Again, I'm labeling as 1, doesn't matter actually, just like to separate it from other elementary matches. Inverse elementary operation is going to look like what? Well, since it's multiplication of the first row by 1 over 5, it's going to be 1 over 5, 0, 0, 1. And what is interesting, that if you understand that if you apply row operations, like for example, like inverse row operation over direct one or direct over inverse, they're going to cancel each other just by kind of definition of inverse row operation, because they are kind of bringing you back to original matrix. Well, what does it mean? If you apply elementary matrices in like opposite order, for example, you apply elementary matrix E1 to matrix A. We know it's similar to this inverse operation, right? But this inverse operation can be canceled by this inverse operation. And we can apply, instead of it, multiplication by inverse matrix. I'll probably need to erase this arrow to place my inverse matrix. And you are supposed to get matrix A back. It's just like you apply direct operations, then inverse, you get matrix back, and elementary matrices are doing the same, just multiplication. And of course, if you apply this, because kind of, they can be interchanged. For example, if you take matrix A and first apply inverse operation, which is going to be 1/5, then inverse to this one is going to be this one, and you can apply it over and get original matrix. So basically, like elementary inverse matrices are doing same kind of stuff to matrix as inverse row operations. Very good. How are we going to use it? Well, time to prove a theorem which is going to allow us to use it. Kind of theorem is going to be kind of long, so I'm going to scroll up, write down first the condition of the theorem. If reduced row echelon form of square matrix A is IN, we're going to consider special square matrices. Then A and N is expressible as product of elementary matrices. Well, what I'm trying to say. Imagine somebody, well, it's not going to be really like proof, but something like verification of how it works. Imagine that you have matrix A and N, you apply some row operations, and you brought it to IN. Remember, we had a theorem that the matrix can either go to IN, reduced row echelon form, or have a row of zeros. Let's imagine that we don't have that row of zeros. You start working on the matrix and it goes eventually to identity matrix after doing row operations. Remember that each row operation can be represented as a product with elementary matrix. That's what we are going to do. We're going to take matrix A, N, N, and start multiplying it by some elementary matrices, which are doing the same row operations as like operations are doing. So for example, the first row operation represented as matrix E1. The second row operation is represented matrix E2. Well, depending on how many steps we can have the last row operation EK. And eventually, if you apply all of them, you are going to get this identity matrix. Well, just like instead of row operations, we are doing multiplication with elementary matrices, which represent the very same row operations. Well, we apply first row operation as matrix E1, the second row operation, the third, and then the last row operation. Just kind of different way to write down row operations. Now, guys, what we are going to do, we remember that each elementary matrix has inverse. What I'm going to do, I'm going to start multiplying this expression by inverses of like last row operation. So EK inverse on this side and EK inverse on this side. I know that if I multiply direct and inverse matrix, I'm going to have identity. And that's going to kind of cancel EK, but there's going to be the previous one. I'm going to repeat this procedure K times until I cancel this one. What I'm going to have at the end, after like K steps, I'm going to get on this side A and N, well, just because I eliminated all of this. And on this side, I'm going to have E1 inverse, E2 inverse, and lots of them. And the last one is going to be EK inverse. It's like I applied the same elementary operations in inverse order. Like first I applied the last one and then the previous one, the previous, until I get the first one. Well, very good. If you look now at this expression, you probably can see that on the left side, we have our original matrix. On the right side, we have a product of elementary matrices. We remember that inverses are also elementary matrices. They are not different from actually like elementary matrices. They are just different elementary matrices, but they are still elementary matrices. And the last multiplication, this one, remember if you multiply something by identity, it's just E K inverse. So we have a product of K elementary matrices. And this proves my theorem that A and N is expressible as a product of elementary matrices. What are those matrices? They are inverses of elementary matrices, which are steps in bringing your A and N matrix to identity, or like make it reduced row echelon form. That's very good, right? So we kind of represent matrix A as a product of elementary matrices. Now, very nice theorem, but how are we going to use this theorem to find inverse? Let me write down this question. How to, sorry, my handwriting on the like screen is so bad. How to use it to find inverse. Well, question is like, what are we searching for? Let's first set up the problem. Imagine that we have A and A inverse, and it equals to identity. Somehow we do know that inverse exists, right? Instead of my matrix A, I'm going to use this representation of like elementary matrices. So I'm going to, instead of my matrix A, I'm going to write down E1 inverse, E2 inverse, and so on. Last one, sorry. EK inverse. And now I'm going to copy this inverse, which I don't know, but I know that it exists, but I don't know it. And probably does not exist. So what I have a product of like bunch of matrices by inverse matrix equals identity. What I can do over here, I can do the same process I was doing before when I was proving the theorem. I can multiply this statement by, I'm going to make it a little bit like smaller numbers, by inverses of this side of the matrices. For example, what is inverse of A1 inverse? That's just E1, right? Because they're inverses, they're going to give me identity. If I multiply it over here, I'm just going to write down one. And I can do like k steps. And after k steps, eventually I'm going to eliminate all these inverses, right? And I'm just going to get over here A inverse by itself. And all these are going to turn into identities. And what I'm going to have on this side? Well, I'm going to have identity multiplied by E1 multiplied by E2 multiplied by E3, and eventually, when I finish all the process, multiplied by EK. So actually, if I look at this statement closer, I'm going to see that my inverse is identity multiplied by elementary matrices which correspond to elementary operations we do when we modify our matrix AN to identity, when we do this reducing, like, or Gaussian elimination, Gauss-Jordan elimination. So basically, this is already a recipe of how to get inverse. You take identity and start multiplying by elementary matrices, or we know that each elementary matrix is actually multiplication is equal to row operations. So start applying to identity. Same row operations you apply to matrix A to get this reduced row echelon form. Of course, no one is doing this, like set up sequentially, like doing first take matrix A, do reducing to row echelon form, write down these row operations, and then apply them to identity. You can do them in parallel. Let me show you how to apply it. So you will kind of see how to do it fast. So I'm going to write down first, it's like formally how we do this. We're going to put matrix A here and then put some kind of separator and identity matrix here. So basically we are going to augment our matrix A by identity of the same size and then apply row operations. Yeah, we're supposed to apply actual elementary matrices, but we remember that elementary matrix is multiplication, which is actually exactly the same result as row operations. Row operations are easier to apply in practice than multiplication, though they're giving you the same result. And eventually, you know that after a set of row operations, if they have a goal to reduce A to like identity, we are going to have identity instead of A. And we know that if you apply same operations or same elementary matrices to identity, it's going to produce A inverse. And that's going to be a legal method of finding K inverse. Of course, it exists. I'm going to show it on a simple 2x2 matrix, which is kind of my favorite matrix 1, 2, 3, 4. We already know what is inverse of this 1, 2, 3, 4 from previous section, right? We already calculated, but let's see how this new method is going to work on it. So we are going to understand it a little bit better. So example. Going to consider matrix A as 1, 2, 3, 4. And the question is going to be, what is A inverse? Well, I'm going to start using my method. 1, 2, 3, 4, a little bar, and identity matrix. And just kind of, I'm going to do this row elimination until I turn this one into identity. And this one automatically is going to be turned into inverse. Well, let's see. My first element is already 1 over here, right? I don't need to do anything with it. So I'm going to eliminate this 3. What I'll need to do, I'll take row number 2, right? And row number 2 minus 3 row number 1. Again, you can use this formal multiplication by similar elementary matrix, but doing these row operations is easier in practice. Let's see what is going to be the result. Well, the result after this step is going to be still 1, 2, and the row number 1 is going to stay. What is going to happen to row number 2? Well, first, this element is going to be eliminated because we take multiply 1 by 3, subtract from 3. 2 multiplied by 3 is 6, subtracted from 4 is minus 2, right? 1, this one, multiplied by 3 is 3, subtracted from 0 is minus 3, right? And 0 multiplied by 3 is 0, and it's still going to be 1. So that's my first step. Okay, well, my second step is going to turn this minus 2 into 1. Remember, our goal is to get identity here. So what I can do, I'm going to write down the operation I'm going to do. So I'm going to apply it to row number 2, take row number 2 and multiply it by negative 1 over 2. It's going to turn this element exactly into 1, right? So let's see how it's going to look in practice. 1, 2, 1, 0, 0, 1. And negative 1 half is going to turn this element into 1, but this element is going to turn into 3 over 2, right? Because it's already minus 3 and minus 1 over 2. And the last element is going to be just negative 1 over 2. Okay, very good. So now the last step I'll need to do is to eliminate these 2. How I can do it? I'm going to move down. So I'll need to modify row number 1, right? Row number 1 is going to be what? Row number 2 multiplied by 2 and subtracted from row number 1. Well, let's see what we are going to have. So here I'm going to copy row number 2 because it's not going to change. And then I'm going to modify row number. So if I multiply row number 2 by 2, like this 0 by 2, and subtract it from row number 1, I'm not going to change anything. And that's kind of why the method is built this way. If I multiply 1 by 2, it's going to give me 2. Subtract from 2 is going to give me 0. So I already have identity matrix here. What is going to happen over here? Well, this element, the first one, multiplied by 2 is 3. Subtracted from 1 is minus 2, right? And the last one, multiplied by 2, is going to be minus 1. Subtracted from 0 is going to give me just 1. And if we look at our result, what we see is my identity matrix here, right? And by our theorem, it's supposed to be inverse matrix here. So I can write down that my inverse matrix is equal minus 2, 1, 3 over 2, negative 1 over 2. Well, you guys probably don't remember if it's exact inverse matrix or not exact inverse. Let's kind of check it. Remember, we had a method last class of how to find inverse, right? For direct matrix A. I'm going to kind of apply it one more time. 1, 2, 3, 4. And then how do we build inverse? A inverse is going to be 1 over 1 by 4 minus 2 by 3, right? I'm trying to check consistency of my result with my previous methods. We understand that if matrix has inverse, it's unique, and two different methods must give this unique inverse the same. And what we're supposed to do, we're supposed to switch 4 and 1. So write down 4 and 1 here, and we're supposed to put minus in front of 3 and 2. Minus 3 and 2. And 4 minus 6 is minus 2. So we're basically supposed to divide by 2 every element of the matrix. So this one is going to give us minus 2. This one is going to give me minus 1. Something is wrong. I forgot the minus here when I was writing it down somehow. Sorry, guys. To raise this and write down normal minus 2. Remember, we put minus here. So then we're not going to have minus 1 here. We're going to have 1. And this third element is 3 over 2. 3 over 2. And the last element is negative 1 over 2. So this is the result of section 4. And let's compare it to the result of this section. And we do see that the result is identical. What is good about this theorem is that you can apply it not only to 2 by 2 matrices, you can apply it to the matrix of any size. So if the matrix has inverse, you will be able to find it this way. Well, which brings us to some kind of important conclusions. Which matrices are going to have inverses? Because if we kind of follow the theorem, we see that to find inverse, we have to apply operations to identity, right? And those operations are bringing matrix to identity. But we do know that not all matrices can be brought to identity matrix. Some of them are going to have row of zeros, which is going to be the case when inverse is not going to exist. Well, I'm going to summarize all this stuff in a bunch of theorems unified into one equal statement in the second part of this lecture. For this first part, it's finished, and I want you to practice a little bit with this method. Use 3 by 3 matrices. I don't think that 4 by 4 is going to be a good idea to use because it's going to be very long, but 3 by 3 is going to be perfect to practice. If you do 2 examples this way, you're going to learn this method. Maybe it's going to become your favorite one. Though, I promise you at least 2 more methods of finding K inverse. Okay, that's all for this first part, and I'll see you in the second part.